Archimedes, born circa 287 BCE, Syracuse, Sicily, Italy, died 212–211 BCE, Syracuse, the most famous mathematician and inventor in ancient Greece. Archimedes is especially important for his discovery of the relation between the surface and volume of a sphere and its circumscribing cylinder. He is known for his formulation of a hydrostatic principle, known as Archimedes' principle, and a device for raising water, still used, known as the Archimedes screw. Archimedes probably spent some time in Egypt early in his career, but he resided for most of his life in Syracuse, the principal Greek city-state in Sicily, where he was on intimate terms with its king, Hieron II. Archimedes published his works in the form of correspondence with the principal mathematicians of his time, including the Alexandrian scholars Conon of Samos and Eratosthenes of Cyrene. He played an important role in the defense of Syracuse against the siege laid by the Romans in 213 BCE by constructing war machines so effective that they long delayed the capture of the city. When Syracuse eventually fell to the Roman general Marcus Claudius Marcellus in the autumn of 212 or spring of 211 BCE, Archimedes was killed in the sack of the city. Far more details survive about the life of Archimedes than about any other ancient scientist, but they are largely anecdotal, reflecting the impression that his mechanical genius made on the popular imagination. Thus, he is credited with inventing the Archimedes screw, and he is supposed to have made two spheres that Marcellus took back to Rome, one a star globe and the other a device, the details of which are uncertain, for mechanically representing the motions of the sun, the moon, and the planets. The story that he determined the proportion of gold and silver in a wreath made for Hieron by weighing it in water is probably true. But the version that has him leaping from the bath in which he supposedly got the idea and running naked through the streets shouting, "Eureka! I have found it," is popular embellishment. Equally apocryphal are the stories that he used a huge array of mirrors to burn the Roman ships besieging Syracuse, that he said, "Give me a place to stand and I will move the earth," and that a Roman soldier killed him because he refused to leave his mathematical diagrams, although all are popular reflections of his real interest in catoptrics, the branch of optics dealing with the reflection of light from mirrors, plane or curved, mechanics, and pure mathematics. According to Plutarch, circa 46 to 119 CE, Archimedes had so low an opinion of the kind of practical invention at which he excelled and to which he owed his contemporary fame that he left no written work on such subjects. While it is true that, apart from a dubious reference to a treatise on sphere making, all of his known works were of a theoretical character, his interest in mechanics nevertheless deeply influenced his mathematical thinking. Not only did he write works on theoretical mechanics and hydrostatics, but his treatise Method concerning mechanical theorems shows that he used mechanical reasoning as a heuristic device for the discovery of new mathematical theorems. There are 9 extant treatises by Archimedes in Greek. The principal results on the sphere and cylinder, in 2 books, are that the surface area of any sphere of radius r is 4 times that of its greatest circle, in modern notation. S equals 4 pi r2, and that the volume of a sphere is 2/3 that of the cylinder in which it is inscribed, leading immediately to the formula for the volume, V equals 4/3 pi r3. Archimedes was proud enough of the latter discovery to leave instructions for his tomb to be marked with a sphere inscribed in a cylinder. Marcus Tullius Cicero, 106–43 BCE, found the tomb overgrown with vegetation, a century and a half after Archimedes' death. Measurement of the circle is a fragment of a longer work in which pi, the ratio of the circumference to the diameter of a circle, is shown to lie between the limits of 3 and 10^71 and 3 and a seventh. Archimedes' approach to determining pi, which consists of inscribing and circumscribing regular polygons with a large number of sides, was followed by everyone until the development of infinite series expansions in India during the 15th century and in Europe during the 17th century. That work also contains accurate approximations, expressed as ratios of integers, to the square roots of 3 and several large numbers. On conoids and spheroids deals with determining the volumes of the segments of solids formed by the revolution of a conic section, circle, ellipse, parabola, or hyperbola, about its axis. In modern terms, those are problems of integration. See calculus. On spirals develops many properties of tangents to, and areas associated with, the spiral of Archimedes, i.e., the locus of a point moving with uniform speed along a straight line that itself is rotating with uniform speed about a fixed point. It was one of only a few curves beyond the straight line and the conic sections known in antiquity. On the equilibrium of planes, or centers of gravity of planes. In 2 books, is mainly concerned with establishing the centers of gravity of various rectilinear plane figures and segments of the parabola and the paraboloid. The first book purports to establish the law of the lever, magnitudes balance at distances from the fulcrum in inverse ratio to their weights. And it is mainly on the basis of that treatise that Archimedes has been called the founder of theoretical mechanics. Much of that book, however, is undoubtedly not authentic, consisting as it does of inept later editions or reworkings. And it seems likely that the basic principle of the law of the lever and, possibly, the concept of the center of gravity were established on a mathematical basis by scholars earlier than Archimedes. His contribution was rather to extend those concepts to conic sections. Quadrature of the parabola demonstrates, first by mechanical means, as in method discussed below, and then by conventional geometric methods, that the area of any segment of a parabola is 4/3 of the area of the triangle having the same base and height as that segment. That is, again, a problem in integration. The Sand Reckoner is a small treatise that is a jeu d'esprit written for the layman. It is addressed to Gelon, son of Hieron, that nevertheless contains some profoundly original mathematics. Its object is to remedy the inadequacies of the Greek numerical notation system by showing how to express a huge number, the number of grains of sand that it would take to fill the whole of the universe. What Archimedes does, in effect, is to create a place-value system of notation, with a base of 100 million. That was apparently a completely original idea, since he had no knowledge of the contemporary Babylonian place-value system with base 60. The work is also of interest because it gives the most detailed surviving description of the heliocentric system of Aristarchus of Samos, c. 310 to 230 BCE, and because it contains an account of an ingenious procedure that Archimedes used to determine the sun's apparent diameter by observation with an instrument. Method concerning mechanical theorems describes a process of discovery in mathematics. It is the sole surviving work from antiquity, and one of the few from any period, that deals with this topic. In it Archimedes recounts how he used a mechanical method to arrive at some of his key discoveries, including the area of a parabolic segment and the surface area and volume of a sphere. The technique consists of dividing each of 2 figures into an infinite but equal number of infinitesimally thin strips. Then, weighing each corresponding pair of these strips against each other on a notional balance to obtain the ratio of the 2 original figures. Archimedes emphasizes that, though useful as a heuristic method, this procedure does not constitute a rigorous proof. On floating bodies, in 2 books, survives only partly in Greek. The rest in medieval Latin translation from the Greek. It is the first known work on hydrostatics, of which Archimedes is recognized as the founder. Its purpose is to determine the positions that various solids will assume when floating in a fluid, according to their form and the variation in their specific gravities. In the first book various general principles are established, notably what has come to be known as Archimedes' principle. A solid denser than a fluid will, when immersed in that fluid, be lighter by the weight of the fluid it displaces. The second book is a mathematical tour de force unmatched in antiquity and rarely equaled since. In it Archimedes determines the different positions of stability that a right paraboloid of revolution assumes when floating in a fluid of greater specific gravity, according to geometric and hydrostatic variations. Archimedes is known, from references of later authors, to have written a number of other works that have not survived. Of particular interest are treatises on catoptrics, in which he discussed, among other things, the phenomenon of refraction, on the 13 semiregular, Archimedean, polyhedra, those bodies bounded by regular polygons, not necessarily all of the same type, that can be inscribed in a sphere, and the cattle problem, preserved in a Greek epigram, which poses a problem in indeterminate analysis, with 8 unknowns. In addition to those, there survive several works in Arabic translation ascribed to Archimedes that cannot have been composed by him in their present form, although they may contain Archimedean elements. Those include a work on inscribing the regular heptagon in a circle, a collection of lemmas, propositions assumed to be true that are used to prove a theorem, and a book on touching circles, both having to do with elementary plane geometry, and the Stomachion, parts of which also survive in Greek, dealing with a square divided into 14 pieces for a game or puzzle. Archimedes' mathematical proofs and presentation exhibit great boldness and originality of thought on the one hand and extreme rigor on the other, meeting the highest standards of contemporary geometry. while the method shows that he arrived at the formulas for the surface area and volume of a sphere by mechanical reasoning involving infinitesimals. In his actual proofs of the results in sphere and cylinder, he uses only the rigorous methods of successive finite approximation that had been invented by Eudoxus of Cnidus in the 4th century BCE. These methods, of which Archimedes was a master, are the standard procedure in all his works on higher geometry that deal with proving results about areas and volumes. Their mathematical rigor stands in strong contrast to the proofs of the first practitioners of integral calculus in the 17th century, when infinitesimals were reintroduced into mathematics. Yet Archimedes' results are no less impressive than theirs. The same freedom from conventional ways of thinking is apparent in the arithmetical field in Sandreckoner, which shows a deep understanding of the nature of the numerical system.